Good morning everyone. Today we will discuss about the search techniques in AI. Right? So we know that AI in artificial intelligence, every problem has a solution. Right? So we'll see about in searching mechanism how the solutions are provided, and we'll be discussing about the searching methods with four properties of an algorithm, how it works. So there are two kinds of search based. One is uninformed search and another is informed search. So now comes to what is uninformed search. So uninformed search will work based on no domain knowledge. So there won't be any specific domain knowledge. So which means that it knows the goal state, but it does not have a specific rules to be followed, and it does not even know how to achieve the goal state. So those kind of searching is going to be uninformed search. So what is informed search is it is going to have some of the domain specific knowledge, which means that it knows how to reach to the goal state with an optimal solution. So under this search strategies, we'll be discussing some of the types which is there in the syllabus. So this is the definition what I discussed, which means the uninformed search does not have any domain knowledge about it, right? And it does not uses any information. So to reach the goal state, it does not have any specific information to reach it, right? So this is going to be discussed with few of the uninformed search strategies. One will be discussing about BFS, which is breadth first search, and one is DFS, which is depth first search, and one more is iterative dependent search. So this already you have learned the data structure, right? So what is your breadth first search and what is your depth first search? The new thing is about the iterative dependent search. But we'll see about what is breadth first search, and then we'll see about the depth first search and iterative dependent search. So now what is breadth first search? Before going to that, as I told you the definition of what is informed search. So the informed search is going to use your domain specific knowledge in order to reach to the goal state, right? And in what terms the goal state is going to be achieved is through the heuristic function. So we'll see how the heuristic function is calculated and how it helps to find the goal state easily. So the heuristic is the one which is going to give us the optimal solution, right? And we'll see how it is going to be estimated to find out the goal state with this is, right? And under the informed search, we'll be discussing about the two types. One is greedy search, which is a best first search, and one more is your A star search. So under the informed search, we'll discuss these two types. So coming to the breadth first search. What is breadth first search? It is an uninformed search, right? So this strategy is going to follow by taking the root node and going to explore the shallowest node in the breadth-wise flow, right? We know that how it is being expanded, right? So it is going to take the root node, then it is going to generate the successor nodes, right? So it expand it. So in depth first search, we'll be having a data structure, right? So what kind of data structure is going to be used? It is going to use a queue, which follows a fast in, fast out principle. So the depth first search is going to be implemented with this queue. So the queue data structure, we know that it is going to follow first in, fast out. And here in the AI, we specifically call this before method, which is implemented in queue using a fringe. So we are going to have a data structure called fringe. So fringe is where it is going to hold your nodes, because the search is going to be in the form of either a graph or it can be either in the form of a tree. So we are habituated to make the given graph converted into a tree. So the tree is going to be having a node. So we know that the node starts with the root node, then it is going to have the parent node, then it is going to have its child node. So the search is going to start from the root node, right? And it is going to expand the node breadth-wise, right? So that is where we call it as the breadth-first search. So for example, this is your simple binary tree. So if you take that is A, B, C, D, E, F, G. So these are the tree, right? So this is simple binary search. where it is going to take a node and place it in the fringe, right? So which means the node is visited. So as it is a breadth first search, the node of the successor of A is going to be visited next, which means explored next, which is of a breadth first. So A will be, once it is visited, that will be removed from the fringe and the successor node of that will be added into the fringe. So every time it is going to be added at the back side of your fringe. So here now A is being visited, its successor node B and C is going to be kept in the fringe. So now what happens next is, what is the next node to be visited? As we know that it follows the FIFO principle. The next node in the fringe is B. So it started visiting B. So when it visited B, that will be removed from the fringe, right? And it started exploring its successor node. So what are the successor nodes? The successor nodes are D and E. So and D and E is going to be added to the back of the fringe, right? So now what happens? Again it comes to the D. B and E, right? So now what happens is, after exploring what is there in the queue, which is C. So we know that the visiting is going to be in the breadth first. This is 1, this is 2, then this is 4, this is 5, this is 6, this is 7. We know the order of how the breadth first search is going to be searched, but still we'll evaluate it. So after this, what is next in the queue is C, right? So the C is going to be visited. So after visiting, that will be removed from the fringe and its successor nodes is going to be visited, which is of F and G. So the F and G is going to be added into the fringe. So now what happened next? Still we didn't achieve the goal node, right? So we have to search for the goal node. So it continues the process. Then it's going to search for the D. Now D does not have any successor. It is the child. So it is being removed from the fringe. Then it visits the next, which is of E. E again does not have any successor node, so that is removed from the fringe. So until the fringe is going to be empty with unvisited nodes, it is going to be visited. Then F is visited, right? It does not have the child. So next, finally the G. So the G is our node, right? So this is how the breadth first search will go. So it goes breadthwise in searching your node, right? So this is an example, simple example of your binary tree, right? How the breadth first search will. Now, this is the algorithm where we discuss about how the breadth first search goes. So let fringe be a list containing the initial state. So we know that the starting node is the first node, root node of a given tree. So that will be kept initially in the fringe, right? So that will be the first node which is being visited. Now there is going to be a loop which is going to follow the process. What's the first thing is, if fringe is empty, return failure. So if there is a nodes is being kept in the fringe, then it returns failure. So nothing is there to visit, right? So next what we have to do is, next we have to remove the first node which is being assigned from the fringe because it is considered as visited. Which means that initially we have set some node in the fringe, right, before the searching. So we have to remove it first and assign it the node. If the node is a goal node, you have to check it, right? So if the node is a goal node, then return the path from initial state to the generating the node in order to find the goal node, right? So normally we call the time complexity is the amount of time, right, to find the goal node, right? And about the space. So what is space is about the memory, right? So when we explore the node, when we place it in the data structure and searching for a goal node, the successor nodes all going to be stored in the memory. So this talks about the space complexity. And next is optimal. So we can find n number of solutions, but among the solution, whether it gives the optimal solution, that you have to evaluate it, right? So these four are the evaluation method where we will be discussing in the search, right? So now when we come back to the breadth first search, we understood how the breadth first search will work, what is the data structure used for it, how the searching will be done, right? Now coming to the complete, yes, it is always reaches the goal as it goes to the breadth wise search, right? And make sure that your breadth is finite. So if it goes to the infinite, then there is a problem in finding the solution. So we understood that the breadth first search as it goes for the searching breadth wise, if the breadth is finite, then the state can be defined as yes, it gives the complete, which means that it gives a solution to it, right? Next, coming to the time. So the time complexity is the number of nodes which is going to be generated. So what is this? D is going to talk about the depth of your node, right? So how it derives the successor of your node, right? So B is going to be a node, right? So this is the time is going to be considered as how many number of successor nodes is going to be hit. That depth it is going to be expanded until it finds the goal, right? So it is going to be defined with the order of B to the power of D, right? So where B is the node and D is the depth of it, right? And next is going to be talking about the space complexity, right? So when we talk about this space, when it goes to the breadth first search, it keeps the nodes in the memory, right? So the root node and then the shallowest node, which is the breadth node, that node will also be in the memory to know whether it has again a successor node to be expanded or not. So how much level of depth it is going to be expanded, right? So that much memory it is going to be occupied, right? So it keeps every node in the memory, either in the fringe or on a path to a fringe, because it has to know the path when it reaches to the goal state. It will derive the path from the root node to the goal node, right? So that's the reason it has to keep every node in the either the fringe where we talk about the data structures of a memory, right? So it is also going to be order of B to the power of D, as how much depth it goes, that much number of nodes is going to be in the memory, right? And next is going to be optimal. Since it is a breadth first search, it is going to be guaranteed that it gives the optimal solution, right? So the deeper the solution or the less the optimal. So if the step first is 1, which means that if we have only one level of a depth, then it is going to find easily with the solution, right? So it is going to be an optimal solution. So this is your breadth first search. So what we done, the steps is given here, where first it traverses with the root node, and then it traverses all your neighbor nodes, which is your successor node, and traverses all the neighbors of neighbors again, right, of the root node. So this process is going to continue until it finds the goal node, right? So breadth-wise search is going to be done by expanding all its neighbor nodes until it finds the goal node. So coming to the next strategy, searching strategy, which is your depth first search. So the depth first search is going to always expand with the deepest node. So the problem with the deepest is the breadth first and the depth first is in depth first, if the node goes on with the infinite depth, but the goal node is going to be lies on any of the other net size, right? If it is get it into the infinite loop, then what happens? It can't find the solution, right? So that is a problem in the depth first search. So how much depth it goes, that much complexity will be there in the searching mechanism, right? So here the search, and the expansion is going to be done to the neighbors in the deepest tree, right? So where it is going to follow the shallowest node, right? So which is going to be found until it is seen any unexploded node. It is going to keep on searching for a node until it goes to the goal state, right? So this strategy is going to be again will use with the tree only, but what data structure we are going to use is stack. So we know what is stack, right? So the stack data structure is going to follow last in, first out principle, right? And again we will be using a fringe here. So here it is going to make a depth first search, which means that from the root node it goes to the shallowest node and to the deepest node until it finds the goal, right? So this is just an example how the depth first search is going to work. So here this is a simple binary tree. So what happened here is this is the A, the search starts from the A, then that goes to the left side of the tree which is of a B node, and from there it goes to the D node, and from there it goes to the H node. So this is one deepest. So in the one deepest, if it does not found the goal state, what it does is then it visits to the ith node, backtrack to the previous, then backtrack to the B node, it backtracks to the B node, then it comes to the A node, and again the deepest node J. If J is not the goal node, go to the K node, right, and backtrack it, again backtrack to the A. So here if you observe that this is where we call it as the shallowest node, which is the deepest, comes to the end of the node, right? So this is how step by step how it visits has been given in this diagram, right? So which is the dark shaded one is talking about it is visited and still it is not the goal state, right? So if you observe here A, then it visits to the B, then it visits the D, then after visiting the D, then it explores the H. So H is not the goal node, so then if you observe here this is I, then backtrack to the B, then backtrack to the B, then it comes to the E, right? So from E again J and K, it visits the J, backtrack to the E, backtrack to the K again. So like this, it is going to visit all the nodes until it reaches to the goal node. So suppose here our goal node is G. If we observe, the diagram starts from the A node and starts searching in a depth wise until it finds the goal node of a G. The process is going to continue, right? So this is your deepest depth first search, right? So it's a similar algorithm what we discussed in the breadth first search. Again here we'll take the fringe. For a fringe is going to contain the initial state of the node, which is nothing but the loop, right? And here the loop is going to be continue the process. The same thing first, if fringe is empty, then return failure, which means that no nodes are available in the fringe. If not, if there exists any node in the fringe, then remove it, assign to the node. So if node is a goal node, find if the node is a goal node, then return the path from initial state to the node. Right? So that where we talking about the solution. Else, if it is fails, then generate all successor nodes of the node and merge the newly generated nodes into the fringe. Now we are going to add the generated node to the front of the fringe. So what's the difference in breadth first search? Breadth first search, what we done is we added the successor nodes at the back of the fringe. But when it comes to the depth first search, we are going to add the generated nodes to the front of the fringe. So this is going to continue until the nodes exist in the fringe. So this is same the algorithm which I talk about. It traverses with the starting node, then with the neighbor node, and traverses the neighbor node. Right? Again, the process is going to continue until the goal node is formed. So let us take this as an example of a tree, right? So where it is going to start from the root node, which is of A. So we'll take a fringe, right? So where A because we are going to the depth first.